from Homeworks? Boyd.
I got a little 34 action.
34 action. Sure.
Much obliged.
No problemo. All right. It says the number of grams of carbon-14 denoted C in a certain substance. Yees. I'm assuming that's supposed to be a year. I don't know what a yeast is. What unit of measurement do you suppose a yeast is? Maybe it's yaz. Anyways, is given by the function C of t equals yada, yada, yada. Use this equation to estimate the half-life of carbon-14. So I can see here that C of 0 is the initial amount. So 20 is my initial. So half of that is going to be 10. So I want to solve C of t equals to 10. Now, non-math related question. Do you guys know what carbon-14 is used for?
Well, you told us, but probably not.
Anybody recognize carbon-14 as something you've heard about?
Probably something like
It's that
gasoline.
one thing.
It's that one thing.
It's that one thing that, what is that in the eye, dude?
Silver nitrate.
Radioactive
isotope.
So it is a radioactive isotope, but how do we use it fairly regularly in practice to do something?
Probably like gasoline or something.
No, not gasoline. Not moling.
Nope.
You use it to do carbon dating. So if you want to know like how old some fossil is, one way you can do that is doing radiocarbon dating. So the amount of carbon-14 fixed in the atmosphere is relatively fixed. That gets incorporated into like the cells that an organism builds. After it dies and it stops undergoing respiration, that amount of carbon-14 then starts to decay. So based on the amount of carbon-14 in the organism, you can tell how old something is. Now, you're talking about something then on the scale of like thousands of years, right? You can radiocarbon date stuff that's real old. Why am I bothering to talk about this? Because if I'm looking for the half-life, if I can use radiocarbon dating to date something that's like real stinking old, like as old as the pyramids or older than that, that's going to affect the window that I'm going to choose, right? Mm-hmm. So I don't know what this is. I'm going to put 10,000 as my X max because X is the years. And I'm expecting carbon dating to be able to do like real old stuff. Oops. And then the Y scale, I'm just going to go from 0 to 20 because, well, we're starting off with 20. And when I finish my decay, I'll be down to 0 stuff. So then I'll hit graph and take a look at that. So there's my C14 curve. Oops. I forgot to put the 10 in there. Boyd, what's up?
What did we put for the Y values again for the graph?
Just 0 to 20.
Oh, no, sorry, I meant
the X? I did 0 to 10,000.
Sorry, I meant like the Y1 and Y2 stuff.
Oh, I just did the function and then 10.
Okay.
So then I can just do second, trace, intersect command, enter, enter, enter. And I get about 5,700 E's. Does that feel okay there, Boyd? So again, like having a little bit of context to that helped me pick a window so that I could like conceivably come up with like what's an appropriate amount of X, like that's a tough question. Maybe you did 0 to 100 and you didn't see a darn thing, right?
So, it doesn't like show my graph on here. I mean, it does, but it doesn't show my negative slope. It just shows the line.
So I think this is probably the issue. I think you probably need I think it's probably doing to that power and then putting the x in rather than putting the x in the exponent.
Okay.
And I think that's
Okay.
that's all it
Thank
was. Yeah, no problem. So you're having like that old operating system. You have to be like real careful about stuff like that because it's real dumb about what it's doing. But these are good questions. That's a good thing to find out before a test, right? That you have to put that whole thing in the parentheses. Who's next for questions? Boyd, number 2.
Then I guess 35.
35?
5 going once.
Sure.
So the man in black.
Boyd, are you the only man in glasses in here?
And sold the first man with the whole banner, leave and all the whole potentially.
All right, let's see here. It says the number of students infected with flu at a certain high school T days later is modeled by the function P of T equals yada, yada, yada. What was the initial number of students infected? Well, initial means what time?
So that's 0 days.
So T equals 0. Yep, exactly.
Oh, that's what you would do.
So all I'm going to do is plug 0 in. So e to the 0 is 1. 1 times 49 is 49. 49 plus 1 is 50. 800 divided by 50 is 8. You can come and take a look. I didn't notice anything, but I wasn't looking for it either.
No, I saw him take it.
Did any of you guys, did anybody take it though?
Thank you.
You're welcome.
That was the funniest bit I've ever seen.
I don't think it's 8.
Yeah, I think it's 16 actually.
Oh, yeah, 16. Yeah, 400 is 8. Thank you. Yep.
What?
All right. Shh. It says that, stop talking, please. When, so again, we're solving for a t there. Will the number of infected students equal 200? So I'm solving P of t equals 100. To do that, I'm going to use the calculator. So I'm going to go ahead and do just type my function in. Now this will be a little bit tough to get with your calculator, Boyd, because you have to use like a whole heap of parentheses here. So you'll need 1 parenthesis at the start of the denominator, and then 1 parenthesis for the exponent. So we'll do that. So time, I don't know. Let's just pick 100 or something. And again, we're going from, 0 infected to at least 400. I know the maximum is 800, so I'll just do that. And then I guess we'll go up by hundreds or something. So I did something wrong there. Did I forget the variable? I sure did. Come on, Mr. Kulik. Look at what I did. At least I noticed when I got a horizontal line, I'm like, well, that ain't right. There we go. So there's my population curve. There's my 200 line. Second, trace, intersect command, enter, enter, enter. So about 13.97 days. Or about 14. The school will be closed when the number of infected students reaches 300. How long will it be until the school closes? Well, again, we're just updating this, then be 300. And doing the same darn thing, you know what I'm saying? second trace, intersect command, enter. 16.9. So that's about 17 days. So 17 days after the first infection, or the first noticing at time 0, whatever. Feel okay, Boyd?
Yeah.
Cool. Oh, I'm tired, guys.
Oh my gosh, same.
It's the most participation I've gotten out of this side of the room all day.
Oh, got him.
Bazinga.
It's been rough these past.
Maybe it's the way you're sitting.
It's been rough.
No,
That
I
looks
got, like,
painful.
No. I'm sick, and so my body's aching, so I need to stretch.
Okay. Last call on questions.
You're ready to rock and rumble for the next.
All right. So today, I need your most excellent attention, because what we're going to be doing is a concept that should be reviewed but is not. What we're going to be talking about today, we're going to introduce the idea of a logarithm. So this is a new mathematical operation like a square root or a exponent or sine or cosine. This is a new operation.
Is that the log button on our?
So that'll have to do with the log button on your calculator. Mm-hmm. And you know these questions that we've been trying to answer that we've just had to graph and find the intersections for? The logarithm is going to be the tool that we can use to solve these questions algebraically.
Sweet.
So we'll be able
This
to
is like the shortcut, is what you're saying.
we'll be able to put away the calculator. Well, it's the pencil and paper version, at least. Call it shortcut or whatever. But so what a logarithm is a way to answer an exponential question. So our logarithmic function is going to be able to be, or we're going to use to rearrange a exponential equation. So let's say that we have the exponential equation b to the y is equal to x, where, again, because it's exponential, b is positive and not equal to 1. This is equivalent to the logarithmic equation, log base b of x is equal to y. And because this is the same b, we know that, again, b has to be positive and not equal to 1. So let's kind of look at what this is saying here. So suppose y is like an unknown, right? Say like we're trying to solve an equation like 2 to the x is equal to 8 or something. Well, to find that unknown, if I rearrange this equation using a logarithm, I can say that log base 2 of 8 is equal to x. So that exponent that we don't know, the number, the name of the number for that answer, we can rewrite just with this logarithm, right? So it's basically allowing us to answer these exponential equations. Now, if I look at the specific example I've written, what does x have to be? Oh, come on, guys. 2 and 4. What power of 2 gives you 8? 3. 3, right? 2 times 2 times 2 is 8. Everybody's okay there? We're just doing it on inspection. But, so we know 2 cubed is equal to 8. We know 2 squared is 4. What if we wanted to figure out 2 to what power gives us 6? It's going to be a decimal, sure. Should it be 2.5? I mean, 6 is halfway between 4 and 8. 2.5 is halfway between 2 and 3.
This is when the logarithm comes in.
Yeah, this is when a logarithm comes in. So that value of x should be log base 2 of 6. If I look at that decimal, we can do that on our calculator. So if you look at your 2 log buttons on your main screen of your calculator, you have this log button here, but there's no subscript on it, right? That's not the log button we want. If you press math and you scroll down to the bottom, command A is called log base. So we can, if we pick that, it allows us to put any subscript we'd like in there. So I can write this as log base 2 of 6, and that is the decimal. So if I did 2 to that power, I should get 6, which is what I'm seeing. Okay. Let's do some more practice, kind of using this definition of a logarithm here. So we're asked to evaluate this. So I'm just going to pretend that this number, log base 4 of 16, is y. Actually, let's write it down here so I have a little bit more space to work with. Let's rewrite that now as an exponential equation. So this is like my b, that's like my x, and that's y, right? So I should write b to the y is equal to x. So what power of 2 is equal to 16? 4, right?
Why'd you use a 2 there, not the 4?
Oh, because I just wrote down the wrong thing. So what power of 4 is 16? That's 2. So we know that log base 4 of 16 is just 2. Everybody's okay with that? Okay. So let's do the same thing here. We have log base 5 of square root 5. We're just going to say that's equal to y. How would I rewrite that as an exponential equation then? So what am I going to write specifically?
5 y
To the y. Great. So what does y have to be here? Yeah, why is that?
because the Swiss square root
Square root is the same thing as a 1/2 power. Okay, so here we have log base 3 of 1/27 is equal to y. All right, how are we going to write this?
3 to the power of y equals 1.
Great. So, well, let's think about it for a second. We notice that 3 and 1/27 are kind of look reciprocally because 1 is a whole number and 1 is a fraction with a 1/. So I know the exponent for y has to be negative because it's a reciprocal, right? So then I just need to figure out then what power of 3 gives me 27. 3 to the third. 3 times 3 is 9, times 3 again is 27. So this should be just -3. So far, so good? Okay, the next one, log base 12 of 1 is equal to y. Let's rewrite that as the exponential equation.
12 to the power of y.
Great. 12 to the y is equal to 1. Well, what's y have to be here?
0.
0. Excellent. Remember that any non-zero number to the 0 is 1. 0 to the 0 is indeterminate. Okay. So log base 8 of 8 is equal to y turns into what exponential?
8y is
8 to the y is equal to 8. So y is just 1. Great. So let's look at some observations here. Any log of 1 is going to be 0. Log of any base, if we do log base b of b, that's always going to give us 1. Ooh, we should say nope, I don't want to say that. That's not true. I want to say that, though. And what if I did one more bonus one? What if I have log base 7 of -2 equal to y? What would I write here?
7 y equals 2.
Okay. Well, remember you have a positive base.
Yeah.
Can that ever give you a negative value? No. So what can we say about y? Such a y does not exist. So you can't do a logarithm of a negative. And really, we should say, or 0, right? The logarithm of anything between 0 and 1 is going to be negative. The logarithm, if you're taking the number you're taking log of matches the base, then it's 1. If you're taking the any log of 1, that's going to be 0. And then I want to make one more observation here. You notice that we have that log base b of x is equal to y, and b to the y is equal to x, right? Well, what if I say, okay, this is my value for y, and I plug it into here? I'd get b to the log base b of x has to equal x, right? Do you see what I did though?
Yeah.
I just made a substitution. What is that really saying though? Well, that's saying that the exponent base b is going to be canceling with log base b so that we just have the x left.
So x.
Right, which is obviously that has to be true. If we had plugged it in the other way, what if we had taken this stuff and plugged it in for the x over here? Then we would write log base b of b to the y has to equal y. So what's the observation we can make here?
Y.
Yeah, that log base b and exponent base b have to cancel each other out. So we notice to cancel exponent, well, let's see, that's what we do, sorry. To cancel log base b, we use exponent base b, and to cancel exponent base b, we use log base b. I'm going to just write it that way. This concept here, that these two operations are going to cancel each other out, is going to be the key to doing all of the solving and all of the simplifying that we're going to be doing here later on. Okay. That is, if we remember nothing else about these observations we've made, this one right here is the big one to remember, because it's the skeleton key to answer all kinds of solving problems and all kinds of simplification problems we have yet to run into. Okay? Super important observation there. All right, so a little bit of special vocab here. There's two special kinds of logarithms. The first we call the common logarithm. Which is log base 10. Which we abbreviate to write just log with no base. When I don't write a base, what do I mean? Base 10. The next one, the natural logarithm, is log base e. Remember, e is that decimal that we talked about in the previous sections. And we abbreviate this one to be ln. Now notice when I'm writing my logs, I'm always using like a script L and kind of writing these cursive. I like to do that. My recommendation is you do this as well. I've seen many a student halfway through a problem with a log in it have that log turn into 10g when they print it, and then end up solving for g by dividing by 10 or some crazy stuff like this.
So is ln the same thing as ln on the calculator?
Yes! Yes, and I think this is lunchtime, so let's pause here, go to lunch, and we'll come back and do some more. Up here. So last thing we did was we looked at these new pieces of vocab for natural logs and common logs. So let's take a look at some of these examples. Kind of the same thing we've been doing before, but this time we have common logs and natural logs here. Howdy. So what am I going to do if I have a equals log of 1,000? I can
into log 10.
I can think about, yeah, that's log 10.
Yeah.
So if I write that in exponential form, that's 10 to the a equals 1,000, and I know 1,000 is 10 cubed. So a is 3. How about b? What would I do there?
10a
Well, it's b this time, but yeah.
equals 5. Exotic.
And the fifth root is the same thing as 10 to the 1/5. So b is 1/5. Well, this is pretty easy so far. Let's see. 10 to the c equals 0.01. 0.01 is 1 over 100. Shh. Or 10 to the negative 2. So c is negative 2. D, what's D gonna be?
What the heck is, oh, that's the ln, so that's the log e.
Mm-hmm. And what do I know about an exponent base and a log base?
Oh, that's tracing back to try to mount d is just equal to 5.
Yeah, they'll just cancel out. Mm-hmm. Shh. You guys just came back from lunch. You should have gotten all your gossip out of your system by then.
Dude,
Yes. So this is going to tell you that 10 squared is equal to x.
what?
So that's good. You could write 100 there too if you wanted. Shh. What can I write here for f? Natural log of y is equal to 5.
Well, the natural law is that log e, so it's a e to the power of 5.
Yep. And that's fine right there. You could type that into your calculator and get a number out of that, but
That'll get the job done.
e to the 5th is okay. It's an irrational number, so just like you could write 5 pi instead of like the crazy decimal. You just write e to the 5th instead of the crazy decimal. Now it's worth noting that like we showed you how to do the log bases on your calculator. If I wanted to just do like the common log of 1,000, I can just do the log button and then 1,000.
Sweet.
Or if I wanted to do the natural log of 7, I can just press the ln button right here and then 7.
Calculator's just awesome.
Calculator's really good at calculating.
Indeed it is.
It's almost like it was built to do it.
Yeah, it was a lot.
Yeah, I know. Alrighty. How are we doing? So far, so good?
Yeah.
Yeah.
Alright.
So it's like that big homework set is just all this easy stuff then, practically for majority.
Yeah, a lot of it's going to be,
Quick little
yep.
10 seconds.
Yeah, there's a lot of pretty straightforward stuff.
Sweet.
All right. So we've talked about kind of what a logarithm is, how to evaluate some things using logarithms, how to type logarithms into our calculator. What I want to do next is talk about some properties of logarithms. So we have 4 main properties of logs. The first one is the product property that says that if I do log base b of x times y, that's the same thing as log base b of y plus log base b of x plus log base b of y.
These are good. Do you have tissues?
I don't. You can go to the bathroom and get something though.
It's actually not.
I'm right there with you.
So the quotient property, same idea, except now we're subtracting. The power property,
Is that C the same C from 15.1 or 2 or whatever?
no, that's just like a constant.
Oh, alright.
So those are the big 3, and then there's another one that this was a huge deal when Mr. Kulik was a high school math student, but the advent of your calculators that you have now has kind of made this obsolete. So when Mr. Kulik was a student, we didn't have graphing calculators. You had probably a scientific calculator that had a log button on there, but not a log base button. So if I want to do log base 2 of 3,
You have to do this.
I'd have to do the change base formula and just do like log of 3 divided by log of 2, or natural log of 3 divided by natural log of 2. What the change of base formula does is let you rewrite a log of a fixed base into the quotient of 2 logs of whatever base you choose. So if you had a scientific calculator with a log or natural log button on it, you could still do, log base 7 of 9 or something that you couldn't, But for you guys, you have the log base command on your calculator, so you can just do it, Boyd, your calculator's operating system might be too old it doesn't have the log base button on there.
Yeah.
So you probably will need to worry about the change of base formula. That'll be helpful.
We'll start by it.
All right. In the interest of, the scope of this class, I am going to elect not to do the proof for any of these.
That's awesome.
We're just going to go straight to using these things. So there's 2 kinds of problems that we're going to commonly ask you to do that rely on using these properties. And they're called expanding and contracting, or condensing. So for an expansion, what you do is you do quotient properties first, product property second, power property last. Unless there's some order of operations thing that says clearly I should be doing the power property before this division because there's a parenthesis or something going on. So if I look at our problem in example A, first thing we do is we look for quotients. Are there any quotient properties going on? So if I look at the stuff inside the logarithm, is there any division?
Don't see it.
No. Is there any products going on? Is there multiplication?
Yep.
Yes. Where's the multiplication happening?
4x.
Between the 4 and the x, right? So I can use the product property to rewrite that as log base 3 of 4 plus log base 3 of x.
Awesome.
Cool with that?
Yep.
Okay, next thing I'll do is look to see if there is any power properties.
Not that I'm seeing.
We might have to look a little bit more closely.
Whoa.
There is one, but it's hiding.
It's a constant classified as
What if I thought about 4 as 2 squared? Now do you see a power property? Oh, Mr. Kulek.
the sneaky ones will get you.
That's why I'm showing you the sneaky stuff, so it doesn't sneak up on you again. Come in. Hi, Mr. Whalen. How are you?
Good, how are you?
Good.
Good. Can I steal these 3 football guys for a coach's meeting?
Yeah, that's okay.
Yeah, come on, man.
Are you a football guy?
Yeah, yes.
There's probably more football guys in here, though.
Where's my football? You
Coming out next year?
Sure I can't come? I want to go on next year.
You'd be such a
Can you kick?
I mean, I was in Powder Puff.
Taylor-
I caught the ball, but ran the wrong way.
She's pretty athletic. Like she can run.
Taylor Timko was on the football team when she was in high school.
Yeah, our girls are going out.
She was the kicker.
Oh my gosh.
That was, I don't know,
She is following the Bulldogs.
like 10 years ago or whatever. Okay.
Rosie Runner, feminist trailblazer. Except she picked. Except she got like tackled and like was out.
All right. So let's look at part B. Now it's a lot harder because Bloom's not here to tell us all the answers. So who else? Someone else is gonna have to. Someone else is gonna have to step up
Carry
here.
their own weight.
Yeah.
So a bunch of
Where is Bree?
Bree's
All right.
good at football and or Nathan's good at football, but you need to like try and get at something.
We have log of 3a plus b to the fifth. Again, these are expanding problems. So the first thing I'm going to do is look for a quotient property. If I look in here, is there any division going on?
I'm not thinking.
No, that's the obvious answer. Believe in yourselves. Okay, so the next thing we do is look for a product property. Is there any multiplication going on
That
in that?
3A, the A and B.
How many multiplications are going on?
3 or 4.
I would say 2.
2.
There's a multiplication symbol between the 3 and the A, and there's a multiplication symbol between the A and the B. Everybody agree with that?
Yeah.
So there's going to be 2 product properties that happen. So I have log of 3 plus log of A plus log of b to the fifth. So far, so good? Okay. Now let's look for power properties. If I look at log of 3, is there a power property going on there? If I look at the log of 3, is there a power property in that log? No. If I look at the log of A, is there a power property in that log? If I look at the log of b to the fifth, is there a power property in that log?
Yeah.
Yes. So how would I rewrite that one? Using the power property? The exponent turns into the coefficient, and then everything else just kind of stays the same. And now we're done. Yep. So these aren't like solving problems. It's not going to be like x equals. The goal is just to take this single logarithm and break it apart and write it as a bunch of logarithms. Okay? All right. Here we have the natural log of 2x over the square root x cubed minus 5. So the first thing we do is look for a quotient property. Do we see one? Yes. So we're going to rewrite this as the log of the numerator minus the log of the denominator. So far, so good? Okay. Now I'm going to look in the first logarithm, natural log 2x. Do we see a product property going on there? Yes. Where is it happening? Between the 2 and the x. So I can rewrite that as natural log 2 plus natural log x. Then I'll look at the second logarithm, the natural log of the square root of x cubed minus 5. Is there a product property happening in that logarithm? What would be multiplied together in there?
Oh, I didn't know.
Yeah, product means multiplied. So nothing going on there, so I'm just going to recopy that part. Okay. Next thing we're going to do now is look for power properties. So if I look at natural log of 2, is there a power property there? No. If I look at natural log of x, is there a power property going on there?
Yeah.
What's the power on natural log x? I'm talking about this piece right here.
Oh, no.
There's no power property there, right? Okay. Last piece, let's look here. Is there a power property going on here?
Yes.
Okay, yes. What is the power? It's not to the third. It's not to the 1/3. It's not to the negative third. What does a square root? What is that the same exponent as? It's as a 1/2. So that's the power going on there. Everybody okay there? Is there anything else going on that we haven't covered yet? Who still feels like this is suspicious looking? It's okay the way it is. The reason that is let's use this color. Is that the logarithm operation is not distributive. So the exponent doesn't, that power of 3 doesn't apply to all of the stuff inside the logarithm, so it doesn't count as a power property. And we can't break that up across the addition or subtraction symbols because the logarithm operation isn't distributive. And if you're ever in doubt, you can say, okay, what if I have log of 5, 2 plus 3? Is that the same thing as log of 2 plus log of 3? And I can just look in my calculator to see if I get the same decimal. And I definitely don't, right? So you should know that we can't break up a logarithm in that fashion. And that's a nice check for us, right? This is a new operation. There's going to be some questions. There'll be some doubt about, hey, what can I do with this again? Yeah. All right. What if we want to go the reverse direction? What if we want to do condensing? Well, here we're going to go the opposite direction. So here we're going to be looking to do power properties, then product properties, and then quotients. So the idea here is we're going to take many logs and rewrite them as a single logarithm. Okay. So to look for, first thing we're going to look for is power properties. But this time, since we're going the reverse direction, instead of looking for an exponent inside the logarithm, we're going to be looking for coefficients in front of the logarithm. How many power properties do you see? Should see 2. Is everybody okay with that? So log base 4 of x is just going to stay the same. The second logarithm, the coefficient of 3 becomes an exponent on the y. And in the third logarithm, the coefficient of 2, I want to look at something real quick. I feel like I copied that down wrong. Oh, no, okay. That's fine. Becomes an exponent on the x. So far, so good? Okay. Next up, we're going to look for product properties. So when we were expanding, we were looking for multiplication inside the logarithm. That was our cue for a product property. Now, when we're condensing, we're going to be looking for addition in between the logarithms. Do we see any product properties going on here? I see a product property happening between log base 4 of x and log base 4 of y to the third. The other thing I need to check is just to make sure that the bases on my logarithms are the same. That's a requirement for these properties. They are, so I can combine those together to be log base 4 of x times y to the third. The last thing that we look for now is a quotient property. So when we're expanding, we are looking for division inside the logarithm. When we're condensing, we're going to look at for subtraction between the two logarithms. And much like the product property, the bases on the logarithms need to be the same. Do we have both of those two things? No, we just have the subtraction between two logarithms. The bases are different. This is as good as we're going to do. So that's can't actually combine those two together because the bases are different. So far, so good? Okay. Let's look at the next one. Oh, that was an AV there. Okay. What's the first thing we look for when we're condensing? Not products, powers, right? It's the reverse order, right? So expanding is quotient product power, condensing is power product quotient, just the opposite order. Do we see any power properties going on? You should see 3 of them because we have 3 coefficients. So 4 natural log of a becomes natural log of a to the 4th. 3 natural log of ab becomes natural log of AB quantity to the 3rd, or you could write it as like A to the 3rd, B to the 3rd. That's okay also. And then I have plus B to the 2nd. Everybody's okay there? All right. The next thing we look for is product. It's right up here, man. Power product quotient. Is that okay? Okay. Do we see any product properties happening? Okay, so you see there the addition symbol here, right? Which definitely involves this logarithm, but it doesn't involve the natural log of a cubed b cubed, because that one is negative. The one that it actually involves is the a to the 4th. So that's the product property going on there. So I can rewrite that then as the natural log of a to the 4th b squared. And since these were both natural logs, I didn't bother to check the bases because natural log is just all basey, right? The last piece now is quotient. Do we see any quotient properties? Yeah, because of the subtraction going on. So I can write that as a to the fourth, b to the second. The positive piece becomes the numerator over a cubed, b cubed. The negative piece becomes the denominator. Do you notice anything about the fraction that that's left inside? We can reduce that, right? And that can just turn down into natural log of a over b. Okay, so let's just write a hypothetical here. So if we have, say, natural log of x minus natural log of y, this is what I would do, is I would think about this as -1 natural log of x plus natural log of y. So I can use a product property here. And then use a power property there. And the -1 exponent makes a reciprocal. So I do that. Is the way I would think about that. Does that feel okay? All right. That feels like an excellent stopping point. So I think that allows us to go 37 to 98. I would say, though, you guys should skip 69 and 70. Those are proof questions. I don't need you to do it. I know that looks like a lot of problems, but like a bunch of these are just like literally says type this junk into your calculator, which is not a lot of time, right? There's a lot of like what I would call like 10-second problems in here.
Whoa.
That are not real long.
Like 10 seconds for me.
Well, maybe not the first one, but by like the last one in the problem set, it should, like the last one in that block of problems, it probably is. You know, like you might need a minute to like, okay, what do I need to do with this again? Okay, I do this, and then, okay. And you do, you know, like the first couple take some time, and then it's like, okay, I get the hang of this now. And it becomes much faster. Is that fair?
Yeah.
Like, yeah, they're all 10-second problems for Mr. Kulik, but like, come on. You're not Mr. Kulik.